Hybrid machine learning molecular mechanics, or MLMM, simulations combine the accuracy of modern machine learning protocols with the efficiency of classical molecular mechanics. In this approach, most of the systems, such as the protein and the solvent, is treated with classical force fields, while the region of interest, for example a ligand, is described by a neural network potential, or NNP, trained on high-level quantum mechanical data. This allows one to increase the accuracy of the description of the ligand at a significantly lower computational cost than QMMM simulations. The hybrid MLMM builder generates simulation inputs for MLMM simulations for several softwares. This video demo will demonstrate the general functionality of the hybrid MLMM builder module in CHARMM-GUI. The protein system we will use is the catalytic domain of human phosphodiesterase 5A in complex with tadalafil, as the ligand of this complex is compatible with ANI and MACE. To begin, go to the hybrid MLMM builder, type the PDB ID 1XOZ, and click Next. We want to include the protein and the ligand CIA, and click Next. If we want to modify the protein structure, this is where we would do it. To learn how to use the structure manipulation options, please see the video demos for PDB Reader and Manipulator. Then click Next to generate a CHARMM-compatible PDB file. Once done, you should view the structure to ensure that it was read correctly. Resolvate the protein and add ions to mimic the physiological conditions. If you have any questions regarding this step, please see the video demos for Solution Builder. With default settings, we build a solvated system and begin the hybrid MLMM specifications. At this stage, we can modify heterochains, mostly ligands, that you selected from PDB Reader. Click the ligand you want to modify, then open to import the ligand into the Marvin.js sketcher. You can modify the ligand. Ligand atom coordinates are initialized by finding the maximum common substructure between the input PDB and output ligand structures by aligning the coordinates in the maximum common substructure. With the first ligand embedding option, atoms are included in the maximum common substructure only if the atom type and bond orders match. With the second embedding option, only atom connectivity is considered, which may result in more atoms being included in the maximum common substructure. In general, matching element is the safer choice, but choose matching any if you want to maintain coordinates from the original ligand as much as possible. Next, click Update Ligand to embed the modified ligand into the system using the maximum common substructure finding algorithm from RDKit. You can see the updated ligand coordinates in the pink-colored ball and stick model. Next, click Parameterize to parameterize the modified ligand. If parameterization is successful, you'll see a green check, otherwise a red X will be shown. When all ligands are parameterized, click Confirm Force Field to proceed. On the next page, the system you built is displayed. Protein backbone atoms, bulk water, and ion visibility can be toggled in the molecule viewer on the left. To complete MLMM modeling, you must select which atoms will be included in the ML region. You can select atoms by specifying the segment ID, residue name, and residue ID. Specific atoms from the residue can be added, or you can use the all or sidechain shortcut selections. To include atoms from another residue, click the Add Atoms button. For ligand residues, there's the additional option of selecting atoms in Marvin.js. This option causes the ligand to be opened in Marvin.js, where atoms can be selected graphically and confirmed with the Update button. Repeat the process until the entire ML region is selected. The ML region can be visualized by clicking the Show Selected ML Region button, which causes selected ML atoms to be colored magenta in the molecule viewer. Next, you must choose a neural network potential and software method. Currently, the hybrid MLMM builder only supports OpenMM and Amber, but this will soon be expanded to include more programs. With OpenMM, all NNPs are ANI and MACE. With Amber, the NNPs are ANI. The currently available simulation packages are shown on this slide. On the next page, we can download the generated hybrid MLMM builder inputs. The enclosed README file demonstrates how to use them, but you can ask any additional questions in the CHARMM-GUI forum.